Welcome back to part 3 of this mini-series, Let's Make and Solve a Rubik's Cube in Unity. In the last episode, we added the ability to rotate the cube, so our players could have a good look around it. In this episode, we'll add a cube map and cast our first Raycast at the cube to start reading the faces. We're going to be picking up right where we left off, so if you missed the previous episodes, I would recommend checking them out first. To help us know what colour is in what position, we're going to create a 2D map of the cube faces. We could position cameras all around our cube and project them onto the screen, but in this circumstance that is overkill, and if we wanted to release on mobile, multiple cameras can cause some devices to struggle. Also, when we read the current state of the cube programmatically, we want to make sure that we're reading it correctly. The cube map is going to be a 2D UI overlay that scales with the size of the device screen. In the hierarchy, we can create a new UI canvas and enter 2D mode. Double-clicking on the canvas zooms out so that we can see it. In the inspector, the canvas's UI scale mode can be set to scale with the screen size, and I've set the reference resolution to 1920 by 1080 as that is the resolution of my monitor. As a child of the canvas, we can create a new UI panel game object and scale it down to be the size of a single cube face in the map. It can then be duplicated to build up an image of the side of the cube and adjusted to make sure that it all lines up nicely. The panels are renamed 0 to 8, starting at the top left corner, so that if we loop through them in an array, the indexes line up with the panel numbers. These panels will be the up side of the cube, so a new empty game object, renamed up, is created as a child of the canvas, with the anchor point set to the top left, and positioned over the center of the side. The faces can now be made children of this game object. To build the other sides of the map, we can copy, paste, and rename this game object, then move them back into the correct positions. Down, front, left, right, back. Once happy with the positions, we can create another empty game object as a child of the canvas, called cube map, position it over the center of the map, and child all the sides to this new game object. The scale and position of the cube map can be adjusted in the inspector. That's looking about right to me. Next, we need a way to read the current state of the cube. This will allow us to update the cube map based on the positions of the faces and allow us to know which pieces to pick up and rotate when a side of the cube is being rotated. There are a few ways that we could handle this, but I'm going to take inspiration from the Robot Cube Solver projects and just look at the cube. In Unity, we can do this with Raycasts. As a child of the cube game object, we can create a new empty game object, rays, and reset the transform. As a child of rays, we create separate game objects for each side the rays we'll be looking at. I'm starting with up, and I'm going to give it an icon so that it is easy to spot in the editor. The up rays should start above the up center piece at some distance. 2 world units will do fine. Similarly, the down rays should emanate from beneath the cube. The front rays from the front, the back from the back, the left rays from the left, and the right rays from the right. We could individually position 54 game objects to represent the start points of each ray, but I think I'd rather handle this in code instead. Selecting the cube game object, we can create a new script, read cube. The first thing we do is link up the 6 ray transform game objects to the script, so that we know where the rays start from. Public transform T up, public transform T down, public transform T left, public transform T right, public transform T front, and public transform T back. In the editor, we can drag the transforms from the hierarchy to the matching slots in the read cube script. We only want the rays to read faces of the cubes, so in the project window, we can select the piece prefab and make a couple of changes. First, we can increase the scale of the box collider of each face to 1.1 in the X, Y, and Z axis. That way, the ray will never miss the face we're aiming at and travel through the cube to hit a face on the other side if we click in the gap between the faces. As the rays should only hit the faces, they should each exist on their own layer. Layer 8 is free, so we'll call it the faces layer and set each of the faces to be in the faces layer. Back in the read cube script, as the faces now have a layer, we can assign a layer mask for our raycasts. Private int layer mask equals 1 bitshift 8. This layer mask is for the faces of the cube only. Once we have read the cube, we need somewhere to look after the state of the cube so that we can refer to it in different places in the program. We can do this by attaching another new script to the cube, cubeState. The cubeState script will keep a record of the current sides of the cube in the form of lists of game objects. These are going to be the sides. Public list of type game object front equals a new list of type game object. Public list of type game object back equals a new list of type game object. Public list of type game object up equals a new list of type game object. public list of type GameObject down equals a new list of type GameObject, public list of type GameObject left equals a new list of type GameObject, and finally, public list of type GameObject right equals a new list of type GameObject. Back in the readCube script, as there is only one instance of the CubeState script in our game, we can reference it by declaring CubeState, and then finding it in the scene. CubeState equals find object of type CubeState. We will build up to reading the entire state of the cube. However, to start with, we're just going to send out a single ray to make sure that everything is working as expected. In the update method, first we create a new list that would contain the faces hit. List of type GameObject faces hit equals a new list of type GameObject. Then we create a vector3 ray starting at tfront's transform and a raycast hit. Vector3 ray equals tfront.transform.position, raycast hit. Next we look to see, does the ray intersect with any objects in the layer mask? And fire a raycast from tfront's transform in a right direction relative to tfront that goes to infinity and only hits objects in the layer mask. If physics.raycast ray tfront.right out hit mathf.infinity layer mask. If it does hit a face, we draw a yellow debug ray and add the face it hit to the list. Having this in the update method is expensive, but as we are resetting the list each time, it won't grow past one index, and this is just a quick check to make sure that the raycasts work as expected. Debug.drawRay ray tfront.right multiplied by hit.distance color.yellow faces hit.add hit.collider.gameObject print hit.collider.gameObject.name. So whatever we hit should turn up in the console too. Else, if we don't hit a face, make the debug ray green. Else, debug.drawRay ray tfront.right multiplied by 1000 color.green. Finally, we update the CubeState.front list with the faces hit list, which should either be empty or contain a single face. CubeState.front equals faces hit. If we hit play, we can see in the console that on each frame, front is being printed. Selecting the cube and looking at the contents of the front list in the CubeState script, we can see that there is a single item, front. If we enter the scene view, we can grab hold of the tfront transform to drag the ray around. If it hits a face, the debug line is yellow. If we drag it off the cube, it becomes green. And because we increased the size of the box colliders, the rays can only hit the faces that they see. We're also going to need to update the cube map based on whatever the current state of the cube is. In the Unity editor, we can locate the cube map and attach a new script to that as well. Add component cube map. Here we'll need to know the state of the cube, so we can reference CubeState. Then attach the parent transforms of the cube faces. Public transform up, public transform down, public transform left, public transform right, public transform front, public transform back. In the editor, we can attach the sides of the cube to their respective slots in the cube map script. Now we need a method to update the color of the faces in the cube map dependent on what side of the piece the raycasts hit. I'm matching my colors to the colors I picked for my cube. If you pick different colors, you'll need to match them to here. Void update map, list of type GameObject face, transform side. This method will loop through each of the children inner side of the cube map, the faces we named 0 to 8 earlier, and use the first character of the name of the face at the same index in the list of faces to update the color of the cube map. Int I equals 0 for each transform map inside if face at index I dot name at index 0 is equal to the char f map.getComponent of type image dot color equals a new color 1 0.5 float 0 1 and that makes orange. If the first character is B, make it red, U is yellow, D is white, L is green, and R is blue. I is then incremented to get the next item in the face list. Now we can create a new method set to set the colors of the cube map. First, we find the CubeState object and then use the update map method we just built on each of the transforms, passing in the side of the cube from the CubeState script that we want to compare. CubeState equals find object of type CubeState, update map, CubeState.front, front, update map, CubeState.back, back, update map, CubeState.left, left, update map, CubeState.right, right, update map, CubeState.up, up, and update map, CubeState.down, down. As we are only casting one ray, and we know it is hitting the front, I'm going to comment out all but the front logic for the time being. As we know the list only has one item in it at the moment, we can set this to 0 to only consider the first index. Back in the readCube script, we can reference the cube map script instance. cube map, and then find it in the scene. Cube map equals find object of type cube map. Then we can call cubemap.set to set the color of the map based on the contents of the faces hit list. Now that we know that the raycasts are working, I'm going to put this in the start method instead of the update method so that it only happens once. We won't be able to see the debug rays anymore, but we don't need to. Now if we hit play, a raycast is sent from T-front, hits the center front face, and populates the front list. The cube map is set, which looks at the contents of the front face, and for each item in the front list of panels, it sets the color of the panel to the color that matches the letter F. Of course, we need to know the color of all the faces, not just the middle one, so instead of sending 1 ray, we're going to send 9. That's it for part 3. In the next episode, we'll graduate to reading the entire state of the cube with many raycasts. If you're enjoying this series, then please like, comment, and subscribe, and I'll see you in the next episode.